What's up, everyone? Welcome to today's video. Today's topic of discussion is polarity. Polarity is the property of having poles or being polar. Now, you've probably seen words like poles or polar before, whether you're talking about North and South Pole, polar vortex, things like that. But what I want to really focus on when we're thinking about polarity is something like a magnet. We know that a magnet has both a positively charged pole and a negatively charged pole. And today, when we're going to be looking at bonds and molecules, we're going to see that these bonds and molecules act very similar in that a lot of the times they'll show that they have a more negative and positively charged end to the bond or the molecule. So when we're thinking about this, think like a magnet. Think we're attracting different charges towards the compound to make us more stable or to make bonds with other molecules and things like that. When we're talking about polarity, we've got a couple of things that we need to keep in mind. In order to determine the polarity of a bond or a molecule, we need to know where most of the negative charges are located. So if the negative charges are evenly spaced around the molecule, that's going to make the molecule, or the bond for that matter, non-polar, meaning that there is not a concentration of more negative charges on one end than the other. Everything is evenly spaced and everything is nice and good. But on the other hand, if we do have more negative charges, or if it's unevenly spaced around a molecule or a bond, then it is going to be considered polar. So that's when we're going to start to see a negative and a positive pole. And that's when we know we're going to see some like different bonding areas and things like that. But when we talk about polar bonds or polar molecules, we have something that we call a dipole. Now, looking just at this word right here, I've got a prefix di and then I have pole. The prefix di just means two. So dipole means we have two poles. So if we just read out the definition, it's defined as a pair of oppositely charged poles separated by a distance. So essentially what we're looking at is we would have poles, like this would be my pole right here. We'd have a more negative end and then a more positive end. And we're going to start to see things like this when we're looking at certain structures and certain compounds and things like that. Okay, so just keep this in mind. Polar means that things are evenly spaced, and or non-polar means it's evenly spaced. Polar would mean that it is unevenly spaced, so we have more electrons on one side than the other. So just keep that in mind. Now, we need to revisit a topic that we covered earlier on this year: electronegativity. We had a trends unit where we looked at different trends across the periodic table. We defined electronegativity as the tendency to take in electrons for the purpose of bonding. So essentially, the higher your electronegativity is, the more likely you're going to take in electrons, so that way you can bond with other atoms, other compounds, and things like that. So when we're going to be taking differences in electronegativities to determine whether a bond or a molecule is polar or non-polar, and we do that using the Pauling scale. The Pauling scale runs from 0 to 4.0. And this will be given to you on a test. You'll always be given the electronegativity values, so that way you don't need to memorize them or anything like that. But you should know generally, as we go across the periodic table, our lower electronegativities are in the bottom left corner, so where francium is at 0.07. And as we move across the periodic table up and to the right towards fluorine, we have a high electronegativity. So our higher electronegativities are going to be in this region of the periodic table, and the lower electronegativities are going to be located around this area right here. So just know that these values are going to be given to you, so you don't need to memorize them, but it is good to know that as you go from here in this direction up to the top right, the electronegativities are increasing. So just keep this Pauling scale in mind, and just know that the difference in electronegativities determines whether a bond or molecule is polar or non-polar. Alright, so we've touched on all the groundwork, all the basics that we need to know so that we can determine polarity, but I think it's about time to get into an example or two. So, let's start off with good old H2O. So this is water. We should be pretty familiar with this structure. H2O has a bent configuration because there are two bonding pairs and two lone pairs. These lone pairs are kind of driving these hydrogens downwards, and that's why we have this bent shape like this. Now, water is known to be a polar compound because when we take a look at this, we see that This red area indicates where there's a higher concentration of a negative charge, or where a higher concentration of where electrons are located in the compound. And then these blue areas are kind of where there aren't too many electrons near these hydrogens. So looking at this model right here, we can see that there is a more negative pole around the oxygen in H2O, meaning that this is going to be a more likely spot for oxygen to bond with other compounds, other molecules, and things like that. So this is what it should look like, but let's go ahead and break it down step by step to get to that answer right there. So one thing that we need to note right here when we're finding our differences in electronegativities is that if our differences fall within certain ranges, that's going to determine whether it's polar or nonpolar. So what I like to do is when I'm looking at a compound like this, I like to first write the electronegativity values based on the Pauling scale for each of my atoms in this compound right here. So hydrogen has an electronegativity of 2.1. So I'm going to just write 2.1 under each one of my hydrogens so that I know that that's what the value is for each of them. And then oxygen is right here, and it has an electronegativity of 3.5. So I'm just going to write that right above oxygen. And we're all good. So now we have my electronegativities for each one of my elements in the compound for H2O. Now, we want to find the polarity of a bond first. So we can either choose this H to O bond or this hydrogen to oxygen bond. Either way, the difference is going to be the same because it's just a hydrogen and oxygen. So my hydrogen to oxygen bond looks like this, and then I'm just going to write my electronegativity values above each of these so I can see what the difference between them is. So 2.1 minus 3.5 minus 2.1 comes out to be 1.4. So if I'm looking at this right here, this is the difference in electronegativities. Does 1.4 fall between 0 and 0.4? No, it definitely does not. So 1.4 is clearly greater than 0.4, so what that tells me is that the bond between H and O, hydrogen and oxygen, is a polar bond. Okay? Electronegativity is greater from right here, or it's greater over here than it is over here. So what that tells me is that my polarity is going to run in this direction, that there's a higher concentration of negative charges on this end than there are on this end. Okay, so that's my bond. So basically what we did was we zoomed into this area. Now, I can go ahead and draw my arrows going in this direction because I'm actually going this direction. That's my fault. Going in this direction here. And that indicates that my polarity, most of my negative charge, is actually located in this area on my molecule. Okay, so now looking at both of my arrows for my bond polarities from hydrogen to oxygen, the general direction that both of these arrows are going in is upwards towards this oxygen. So when I'm drawing this, what that tells me is that my molecule polarity, or my dipole, shows that there's more of a positive charge on this end of H2O and more of a negative charge on this end of H2O. So a greater concentration of my electrons are going to be located at the top up near oxygen, just like this. So this is what something that would look like, and just looking in the general direction of both of these arrows, I would say that this is a polar molecule. Alright, so bonds between H and O, polar, more pointing towards the oxygen. The entire molecule now, based on the polarity of both of these bonds, tells me that this is a polar molecule as well. And we know this because water is the universal solvent. It does a really good job of dissolving most solutes. So this is a good example to start with. Alright, so there's that one. Let's do another example. We'll do sulfur difluoride. Very similar structure to water, that it has a bent configuration, 2 bonding pairs, 2 lone pairs, bent configuration, but we're going to see a little bit of a difference in polarity when we look at this one as opposed to H2O. So sulfur has an electronegativity of 2.5, and fluorine, each of these have an electronegativity of 4.0. Fluorines have the highest electronegativity on the periodic table, so this might be one that might stand out to you a little bit easier. once I have my electronegativity values written out by each of my atoms, what I want to do is I want to find the bond polarity between this sulfur and this fluorine. So between sulfur and fluorine, sulfur has 2.5 electronegativity, fluorine has a 4.0. The difference between these two is 1.5. So 1.5 is certainly greater than 0.4. So the bond between sulfur and fluorine is a polar bond. Okay, so it's going in this direction like that. All right, so if I have a polar bond where it's going from sulfur to fluorine going this way, that tells me that most of my electrons are going to be located in this area of the compound. So if I wanted to draw my dipole for the molecule going this way, that tells me that this is going to be more of the negative side, and that by the sulfur is going to be the more positive side, telling me that I have a polar molecule. Okay, so instead of H2O, where we're going towards the oxygen, now my electronegativities are greater in my fluorine, so that tells me that the polarity of my molecule is going to be focusing more in the region of these fluorines, because they have a greater electronegativity value. Alright, so there's two examples where we've got nice polar molecules. Now I want to show you an interesting one that we will come across sometimes, and this is probably a familiar compound as well, CO2, carbon dioxide. Alright, so and we can go ahead and follow the same procedure that we've been doing for our other compounds before these. So we're just going to write our electronegativities. Carbon has an electronegativity of 2.5. Oxygen has an electronegativity of 3.5. So I'll just write that above each of these. Okay? So let's just find the difference in electronegativities now between the bonds, one of the bonds of carbon and oxygen. Carbon, 2.5. Oxygen, 3.5. The difference here is 1.0. So this value, 1.0, is certainly greater than 0.4. So the bond between carbon and oxygen is a polar bond going in the direction of oxygen. Okay, so the difference here is 1.0. So just draw my arrows from carbon to oxygen. So this is where things now get a little bit interesting and a little bit different than we've seen so far in this video. So the difference between this carbon and this oxygen is 1.0, like I wrote up here, but it's also 1.0 from this carbon to this oxygen. So earlier in the video, I told you that if negative charge is evenly spaced around the molecule, then it is nonpolar. Okay, so looking at these two, we've got 1.0 difference, 1.0 difference going in opposite directions. Essentially what you can think of is that these cancel each other out, because the same pole going to this oxygen is going to this oxygen as well. So we can say that these cancel each other out, making this a nonpolar molecule. So what this shows us then, it is possible to have polar bonds within a molecule, but the entire molecule itself is nonpolar. So this does show us that it is possible. We have a polar bond, two polar bonds, but since they're both going in opposite directions, they balance each other out, evenly distributed throughout the entire molecule. So this is a nonpolar molecule. Alright, so this one is a good example of showing that we can have a polar bond and a nonpolar molecule. Alright, I'm going to show you one more example where this looks very similar now to carbon dioxide, but we'll see how this becomes a little bit different once we start to break down our bonds. So we've dealt with compounds where the bonds between the central atom and the outer atoms are the same, but now we've got two different bonds going on within this compound. Okay, so we'll just write our electronegativities. Carbon 2.5, sulfur 2.5, and oxygen is 3.5. So first I want to find the electronegativity difference between sulfur and carbon. Sulfur 2.5, carbon 2.5. The difference here is 0. Okay? So, looking here, if my difference falls between 0 and 0.4, that considers it to be nonpolar. So this bond between carbon and sulfur is a nonpolar bond. So right here, there's really no polarity at all. We don't need to draw an arrow, we don't need to draw anything. This difference is 0. Alright, now let's find the difference in electronegativity between the bond of carbon and oxygen. We just did this for carbon dioxide, but good for practice. 2.5, 3.5, the difference here is 1.0. Of course, greater than 0.4, so this is going to be a polar bond. And so now what that tells me is that going in this direction, we've got more of my electron concentration being around the oxygen over here, which tells me then that my dipole runs linear in this molecule, where most of my negative charge is going to be on the end of the oxygen. Most of my the more positive end is going to be near this sulfur. Okay? So hopefully I've shown you a few examples that will help you understand the topic of polarity. The main thing that I want you to remember is I want you to remember to find your electronegativities between your elements, between your atoms in the compound. If that difference falls between 0 and 0.4, that's going to make it nonpolar. If the difference falls greater than 0.4, that makes it polar. Using those different polarities of your bonds, that should show you in which direction your compound or your molecule is going to go with its dipole. And then from there you should be able to tell me whether it is going to be a polar molecule or a nonpolar molecule. I really hope this video helped out. If it did, make sure you leave a comment below. Ask me for some requests on any other videos that you want to see. If you want to see more examples, I can show you more examples as well. Until next time, I'll catch you later.